So thanks everyone for tuning in. I also want to thank John and Cody for organizing this nice seminar series and giving me the opportunity to speak here. I will present some recent work that I did with Thomas Grimm, together with one of his excellent PhD students, Damian van der Heijster, both in Utrecht as well. And yeah, as John said, I will tell you about general asymptotic Calabi-Yau periods. So let me start with some motivation first. I want to say that Calabi-Yau threefold period vectors are an important ingredient in string compactification. So the period vector is just the integral of your unique 3-0 form over an appropriate basis of 3 cycles. And it still depends on the complex structure moduli that I denote here by T. So if you look, for example, at 4D theories that arise from type 2b compactifications, you will have a kinetic term for your scalars in the vector multiplet that looks like this. And these T's here will be identified with your complex structure moduli, while your field space metric will be identified with the geometric Kähler metric, which in turn depends on the period vector. Then you can also, for example, look at the superpotential, which is the pairing of the 3-form fluxes with your period vector. And so it's desirable to have a good understanding of the structure of the period vector. But in general, this is quite a complicated function of your complex structure moduli. So our goal in this paper was really to understand the structure in asymptotic regions in the moduli space, because there you can actually say more things are more constrained, and then to construct models of the period vectors for computations using principles of Hodge theory. So here's a brief outline of my talk. First, I will start with some background information. I will tell you what I mean by boundaries in complex structure moduli space. Then I will say a few words about the concept of variation of Hodge structure. Then I will present you some results from asymptotic Hodge theory, which allow you to simplify things near the boundary. So I will tell you what the near boundary expansion of the period vector looks like, and how you can classify these boundaries, and also how you can associate some simple data to these boundaries. This data will be used in the third part of my talk. I will tell you briefly how we use this to reverse engineer back from the simple data period vectors, models for period vectors, and I will give you a specific example. So let's start. So in the complex structure moduli space, you have divisors that are locally defined by some equations at I equal to 0, where you Calabi-Yau develop singularities. Now you have this familiar picture here where you have 2 cycles. And if I, for example, take first coordinates at 1 to 0, the first cycle on the left here might shrink, and I have a singular geometry. Now I could also take another coordinate like Z2 to 0, and the other cycle here on the right might shrink, also developing a singularity. Now I can go to the intersection of both divisors, and on this intersection I would have both cycles degenerate, and so I would end up with this singular geometry here. Now it's a general result that you can always locally describe the intersection of n such loci by normal crossing divisors, which just means that upon relabeling your coordinates, you can just locally express this as Z1 up to Zn equal to 0. Now in this talk, I will frequently switch between the t coordinates and the z coordinates, which are related in this fashion, and the t coordinates are the ones which are readily defined with the scalars in your vector multiplet in the type 2b scenario. Now, we refer to these loci as codimension n boundaries in the moduli space, and probably the most famous example of such a codimension H21 boundary would be the large complex structure point, which is crucial for mirror symmetry. So as you move through the complex structure moduli space, you actually change your notion of what you call holomorphic. As a result, the Hodge decomposition on the middle cohomology of your Calabi-Yau varies. So you have your usual HPQ decomposition like this. Now the total space, of course, stays the same, but the orientation of these subspaces now varies. You can think of the orientation of the complex line spanned by your unique 3-0 form, which now changes as you move through moduli space. Now, the crucial insight is that this variation is not arbitrary, and you can actually capture this nicely in terms of the so-called Hodge filtration. So this is just a different way of capturing this Hodge decomposition, and I give you the relation between the two here on this white window. And so the statement is that if you take the derivative of these FPs with respect to the complex structure modular, you end up in FP minus 1. So you just move down by one step at a time by applying the derivative, and this property is commonly called horizontality. And maybe you know the more familiar special case of it, which just says that the derivative of your omega with respect to the complex structure modular has a 3-0 piece, but also a 2-1 piece. Now there is more structure, so you say that the variation is polarized if further two conditions are satisfied. So you first have an orthogonality condition, which is just this pairing here, where the pairing is given by the normal integration of forms over your variety, over your Calabi-Yau. And you have a positivity condition just telling you that for every element omega, if you pair it with its conjugate, then this quantity here is positive, not vanishing. And these two conditions are generally known as the Hodge-Riemann relations. Now, it is an important fact for Calabi-Yau, and will be important for us, that you can span the entire middle cohomology by taking derivatives of your 3-0 from omega. So now let's move on to asymptotic Koch theory, which tells you how things even simplify, are further constrained next to the boundary. So the period vector captures the variation of Hodge structure, and it's particularly constrained in these asymptotic regions next to the boundary. So as you circle a single boundary component defined, for example, by zk equals 0, the period vector undergoes monodromy. It just means that it transforms with some matrix here, which in our case sits in the symplectic group. And then it's the fact that these monodromies can always be made unipotent, which means that if you consider the combination tk minus the identity up to some power, you get 0. Now, with using these monodromy matrices, you can define the so-called log monodromy matrices, which will be nilpotent due to the unipotency property. Now, so what you can do is, given the codimension boundary, you can associate n log monodromy matrices to it. Now, it was shown by Schmidt that next to the boundary, the period vector admits an expansion like this, where here you have this exponential Tn with this log monodromy matrices. Then you have these coefficient vectors, A0, A1, and so on here. And you have here some exponential dependent term on the T coordinates. Now you can write this more compactly in the following form using this gamma function. And so here the A0 is an element of so-called mixed Hodge structure, which I cannot tell you a lot of details about, but it captures the splitting of H3 at the boundary. You can no longer just describe by a usual Hodge decomposition because of the singular nature of the geometry. Now this e to the Tn generates the polynomial behavior in the T's polynomial because this is a nilpotent operator. And this gamma vanishes at the boundary, so for z equals 0, and it generates the exponential terms by acting on A0. This is why we call it the instaton map. Now this name would just be fully rigorous at large complex structure, where indeed all these exponential terms have interpretation in terms of instantons on the mirror side. Now the nilpotent orbit theorem by Schmidt guarantees you that the polynomial approximation that you get by dropping this gamma factor, which looks like this, it still defines you a proper variation of polarized Hodge structure, which means that the Hodge-Riemann relations are still satisfied by this. Well, in general, these results and these expansions, these hold for all the elements of your filtration, so of your middle cohomology. So you can, in principle, get a full basis for the splitting of H3 at the boundary. So what we do in practice is use the derivatives of the period vector, and then from this you can extract the so-called limiting filtration. So a crucial and important fact is that all these possible splittings are classified, which we will see in a bit. But for now, what we have is that given a codimension and boundary, you can associate some nilpotent orbit data which captures this boundary structure, and this will just be a bunch of matrices and this limiting filtration, or in some sense, just the basis of the splitting. Now, working with this polynomial approximation has already led to some promising results in physics. Here, just to name a few people who have worked with this. So where is the problem then? Because actually we wanted a simpler expression, now we have one, but in some cases this is not enough, because actually, so the mathematics results, they are for all the elements of your middle cohomology, but in physics we only work with the period vector, which is the representative of your 3-0 from omega. And the information about the lower HPQ spaces, so the H21 and so on, enters through the derivatives. So if you consider, for example, your Calabi metric, which has this expression here, you can see that it depends on the derivatives of the period vector. So now just using pi polynomial gives you certainly a simpler expression, but it might result in actually your metric being non-invertible anymore, which is well, not what we want. So you can actually make this more precise, and this is due to the fact that you are no longer guaranteed that you can span the entire middle cohomology just from derivatives of the polynomial approximation. The easiest way to see this is just by brute force applying the derivative operator, and this will pull down for you these factors of n here that then act on A0. Now, I haven't told you yet how exactly they act, but here are already two extreme cases. So there is the conifold type, which for which all the ni acting on these A0s give you 0. So there is literally no information that you can recover from the derivatives. Everything got kind of thrown away, truncated when you took this polynomial limit. Then there's the other extreme, which is the large complex structure type, for which any combination of even 3 of these matrices acting on A0 gives you something non-trivial. This does not mean that there is no crucial information in the exponential terms, just means that the Hodge theoretic information is captured by the A0 part. And we actually know that the exponential terms capture the instantons for the mirror side. Well, and most cases actually in between these two. So most cases require some exponential corrections to the polynomial part. And so we have to rely on this instanton map gamma to generate at least some terms for us. So now, to make this more precise, one should understand the action of n, try to understand or know the action of ni and gamma on A0. This can actually be done by looking at the different splittings. So I cannot go into much detail, but they can be nicely represented by diagrams, by so-called Hodge-Delinda diamonds. So these look like this, and the different subspaces are labeled by dots, and then the dots are labeled by their dimension. If there's no label, it just means that it's one-dimensional. And there are actually 4 main types, 1, 2, 3, 4. And these, depending on the location of your A0 in this splitting, this defines for you your type, and then the subtypes, they are just linked to the dimensions of these middle space subspaces here. These dimensions are related in the following way, as you can see here. Now, the crucial thing here is that your log monodromy matrices act by mapping vertically down. And so you can see, for example, here that there is no place to map to. So any log monodromy matrix acting on A0 will just give you 0. So this is exactly this conifold type case that I showed you previously. And then for this type 4 singularity, if D would be H21, the dimension of your moduli space, all these points would be aligned. And if in addition, your log monodromy matrix is Ni, acting on A0 would span you this space of dimension h to 1, then this would be a large complex structure singularity, large complex structure point. And then you can, like by this graphic argument, convince yourself that you can basically span your entire Hodge Delinda diamond. But for most cases, you can see that just having A0 will never get you all the columns of this diamond. And so basically if you want to span your entire three-form cohomology, you need to be able to span this entire space that arises at the boundary. So away from large complex structure, you really need some of these correction terms, AI. And you can also easily get a lower bound of the number of terms you need by just naively counting the columns of these diagrams with the multiplicities. And so you really need to rely on this map, on this gamma, to generate some correction terms. And so this map gamma will exactly be composed of maps that allow you to kind of map to the right in these diagrams to get to other columns. So this generates, acting on A0, these terms here, which then will sit in the different columns. So so what is also nice about this classification is that, well, for a fixed number of moduli, you can simply list all the possible cases. So for the one modulus case, there are actually only 3 possibilities. There's the conifold singularity, the so-called Turing degeneration, and the large complex structure type. Now for 2 moduli, things get a little bit more interesting, and you actually have 4 classes, and these 4 classes have different subtypes. So here the notation is that, so on the left and on the right, you have the singularity types that correspond to the individual divisors, that 1 equals 0 to 0, z 2 equal to 0, and in the middle you have the singularity type associated with the intersection. So you can see here that you don't have all the possible combinations that are there, and this is actually due because there are some further constraints that arise from polarization conditions, and this list has been worked out by mathematicians in 2019, and this is actually all you can have for 2 moduli. And this Coney LCS class is kind of the equivalent of the singularity types that was used by these groups. So they do it for the 3 moduli in the 3 moduli setting, but it is kind of the equivalent where they constructed flux vacuum with exponentially small superpotentials. And this 2,1 class, for example, has also as its members the kind of singularities you need to do the geometric engineering of this hypercritical limit. So you take the local limit for your Calabi-Yau and so on. And of course, you have the large complex structure class. Now, okay, now we have a list. There's a list of all the possible singularities that you can have. Now, how does this boundary data look like? I actually told you already how you can associate this nilpotent orbit data, but you can actually do more and get some simpler data which captures this structure. So you do this by using the so-called SL2 orbit theorem, which provides you an algorithm to reduce this nilpotent orbit data further to some distinguished basis of twiddle, which is just a rotation of your limiting filtration F0p here by this rotation operator delta. And you also get a sets of SL2 triples, so one set for each log monodromy matrix that you have, and these just satisfy the standard relations. And so what is nice about this SL2 data is that this is really easily constructed from representation theory. So for each boundary, you can easily write explicit matrices down and everything. And so this is really the perfect starting point for our analysis to, for each class, you can take this data and reverse engineer the period vector. So let me just say a few words about this. So as I said, we start from this SL2 data and we work back to get the essential terms of the period vector. By essential, I mean the terms, the minimal terms that we need to get a well-behaved Kähler metric and so on. Now, so we start with this SL2 data. So we write this down for each of the different classes of singularity. Then we have to construct the most general rotation operator, and we use you can use an algorithm to get from these triples back the original log monodromy matrices. So we get the nilpotent orbit data for each type of boundary. And then we use this gamma map to incorporate the filtration of the whole filtration into the F03 part, so into the period vector, if you want. And to just get some models that give you some well-behaved physics. So here I just show you briefly what this looks like for this Coney LCS example. So this class has two members and you can treat them in one go, which is actually true for every class. So this saves you a little bit of work. So this is what these ingredients look. So here is your A0, your distinguished A0. Then you have your rotation operator delta, the two log monodromy matrices, and this gamma, which has as component these holomorphic functions that vanish at 0. And then on top of this, you have some constraints that arise from the horizontality property. And so implicit, but already here you can see some.
Brice, you froze a little bit for maybe the last 30 seconds. Just want to
last 30 seconds.
Yeah.
Okay. Yeah, my internet. So was I on this slide?
Yeah, you were.
Yeah. Okay. So I was saying that basically you have this, just as an example, this Coney LCS class, which has two members, and you can treat them together. So you don't have to treat each member of a class separately. It saves you some work. So this is just what the ingredients then we construct look like. And so you have this gamma with these component functions, which are just holomorphic functions that vanish at 0. And on top of this, you have some constraints that you get from the horizontality property that will give you some differential constraints on these functions here. Now, you can put this all together for the moment without imposing the constraints, and you get this vector here where we leave the component function still implicit. As you can already see some nice structure here that you kind of expect when you work with this for a little while. So for example, you see that there is no log z term at leading order, so which is kind of characteristic of this conifold type boundary, so which is nice because what you expect, because you have here this conifold type singularity. Then you have a log z2 cubed, which is also what you kind of expect from large complex structure type boundaries, so that you can also already see at this level. And then you can just pick a simple ansatz and you can solve the constraints and actually write down the complete kind of minimal model. And now, so you distinguish between the two members just by setting either this parameter n here to 0 or some non-zero rational number. And then this A here controls for you your correction terms that you need for some well-behaved Keller metric and so on. And these deltas are just some also real, and they are just the components of this rotation operator. And while in our paper, we give this construction for all the 1 and 2 modulus cases that are not of large complex structure type, because the large complex structure is kind of understood what the period vector really looks like. So let me finish with some outlook. So it would be interesting to run this program for also more than 2 moduli, because there is actually no type 3 boundary for less than 3 moduli. So you also, you just don't have that. Now you could also, if you want to do F-theory, generalize this to think about generalizing this to Calabi-Yau fourfolds. Conceptually, there's no, it's possible. It's just, you have to do the work. And then ultimately we want to use our models for some computations also in the swampland program. And it would also be interesting to relate this approach to the Picard-Fuchs approach. And there's already some ongoing work in the mathematical community by these people here. And so this might be interesting to get like further constraints on these unfixed coefficients, which we still have, and so on. So that was all I had to say. Thank you for listening.
Great. Let us all thank Brice for his very nice talk. While we wait for questions, I think I have one. So you described how these singularities are described by data, SL2 data.
Yeah.
Is it a finite classification, or is there like an upper limit, or?
For a fixed number of moduli, you have a finite number of possible cases. Yeah.
And that just scales up more and more with.
Yeah. Now, I mean, as I. For example, if you look at this list, which is here, I mean, I guess the polarization constraints will become more and more severe, and there are less and less combinations. I mean, you get more types, but so you cannot combine every singularity types together as you wish. I can imagine that if you go to higher moduli, then this becomes more severe, these constraints.
And would you expect that eventually it asymptotes to a?
No. Okay, I would not say so, but I also don't have a very informed opinion about this. I mean,
okay.
Yeah.
Cool. Thanks. Are there any other questions? Well, with that, let us thank Brice again using an emoji of choice, and we'll move on to the next one. Thanks a lot, Brice.